Hey everybody, it's Bruce and the dog on the floor, and today we're going to talk about using labels to make beautiful predictions. And as you'll remember, last week we talked about building categorical data that would be the output of one of our probabilistic models. And that might return something like 30% for fizz, 20% for buzz, 50% for fizz buzz, and 0% for other. And that's called a probabilistic model, but it's not the most user-friendly thing that we could do. So instead, we're going to write a function and map those predictions onto some labels. It's going to be pretty straightforward, so let's go ahead and get started. So let's look at the code that we had last time. So we have the inputs, and these are in the form of helpful data attributes that are in a numeric format that are based on our input. And remember, this is a game, this is a counting game, and so the input is an individual count, right? And then the output is a probabilistic model where 1 is yes, this is true, and 0 is no, this is false. Well, what's going to happen when we have our training data is going to have 1s in some places and 0s elsewhere. And those are going to actually match real world observations. But our learning models, they're not going to be quite so sure. So we might have data that looks like this. So for example, I might have some data that looks like 0.1, 0.2, 0.4, and then what's left? That's 7, 0.3. So this is very weakly predicting a fizz buzz. So this is fizz buzz, and other, right? And so I could say this is going to be the probability of fizz, the probability of buzz, the probability of fizz buzz, and the probability of other, right? So this is my input. This is what each output is going to look like. And then we roll up a bunch of inputs for the training and so the inputs and outputs for the training, and then the inputs for the test. And we really don't need the outputs for the test because we're going to convert those into a human form, and that's what we're going to do in this section. So what we're going to do is take these things and we're going to build labels for them. Though the last one, we really don't need a label because we're going to use the N instead, right? And so let's build the labels for the first three. So labels, and this is an array of words, and this is fizz, buzz, and fizz, buzz. So this is a sigil, and sigil is just a function, sigil underscore lowercase w, and this is going to produce a list of individual strings. And so think about how we might convert this list and these probabilities to a single answer given an input. We're going to do that next. Okay, so now we have the train inputs, the train targets, the test data. So let's call this the test inputs. And now we need to build the def test outputs. Okay, so the test outputs are going to be a little bit different because we're going to use the Axon framework to actually generate the data that we want, that we want to use, right? So the test outputs, remember when we make a prediction, we're going to need the model. So effectively what we're going to be doing is making a prediction and translating that prediction into basically unfriendly data or the probabilistic data, and then we want to translate that unfriendly data into human readable data so we can quickly look it over, right? So what I'm going to get is a model, and to make a prediction, I need to know what parameters we've trained to. Remember, we are trying to tweak those mx plus b parameters so that I have the line that makes the perfect predictions. But what data am I going to pass it? Well, I'm going to pass it a data set, and I probably want to use the test inputs like that, right? And so to make a prediction, remember I'm going to use Axon predict, so model, and then I'm going to feed that to axon.predict. And remember that takes the model and the params and the data set, right? This pipe probably didn't buy me anything, so let's just take let's take a prediction, and then let's pipe that to, let's see, that's the predict. Okay, so what's coming out of here is data that looks like this. But instead of the tidy version where we're looking for ones, we actually just want the largest value. But we want to do this over a tensor, right? So the tensor is going to have rows and columns. And so we want a function that's built to get the maximum probability, and that's called nx.argmax. Usually we've been keeping our features along that, not the axis 0, but the axis 1. So let's do it that way. And then what I want to do is take these, and I basically want to stitch up labels with numbers, right? What I want to come out of this is a whole bunch of labels with the numbers, and then I could take either the label, or if there's no label, that means it's an other, then I can use the number instead. So let's write that labels with numbers. Labels with numbers, and that's going to take the prediction. Effectively, I'm taking that prediction, and then I'm going to convert that to a list. Let's see what that looks like. Okay, yeah, so you can see that this is a nx to, yeah, could be an nx to list, but I really want an nx to a flat list because that's going to fit the shape of the data that I want to create, right? Nx to flat list. And then, okay, so what I'm coming out of here with is a bunch of individual predictions in it. And I want to take those predictions and I want to stitch them up with an index. Because look, all of our inputs our data sets start at 1. It's not always going to be true, but it is in this case. And so that makes it pretty easy to actually track back to the input values that we're using to generate these targets, right? And so what I'm going to do is actually pair each one of these predictions with an index. And then if I actually want to use that number, I can use the label, I'll use it. But if there's no label, then I'll just use the index instead. So let's write a private function to do that. And why am I mapping? Well, because this is a tensor, there's more than one of them. I just want a label or a number for each one of those. And I'm going to write that in a private function just to keep things simple. Label or number, and this is going to take, yeah, this stitched up thing, right? So this is going to take the label or nil, right? Because this could be any one of those 4 categories, and it's going to walk off the end if it's a nil, right? So it's a label and it is an index, right? So what do we want to do? We want to do the at labels, and then we want to get the label at the index. And we don't want to be too restrictive here. We want this to be able to fail with a nil because one of the values that this could return is 4, right? So if it returns a 4, we don't really want to use this label. We want to instead, and I'll use kernel.or to basically nil protect me in my code where I need to. And in this case, what I'm looking for is that index instead. And so I could be a little bit defensive with this code if I wanted to. I could write a function that actually picked off the label, which might be other. And if it were other, I could replace the other. But I think that this is going to work just fine for my purposes. I've already created from real world data train inputs and train targets. And I also have test inputs, and I can build those test outputs, right? So what we're going to do is we're going to create the test inputs as before, and for the test outputs, we're going to make a prediction. And then based on that prediction, pick the biggest one of every single of those. So here I have a whole bunch of indexes of the largest probability. So I have 0, 1, 2 for FizzBuzz and FizzBuzz, and I have a 3 for something else. And then I'm going to pick off the label at that point. If it's a label, great, I'll use it. If it's not, I'll go ahead and graft on the index instead. So that's what we're going to do with this program. And what we've done is built a pretty prediction based on the labels in our product. And that's going to allow us to rapidly scan through and understand the data that our model has created. And that's an excellent thing. For Bruce and the dog on the floor, this is Coaxial Learning.